Hey everyone, thanks for coming to my talk today. And it's all about bridge building between adaptation research and coral models. So I'm not going to talk to you too much about our actual results. I'm really more focusing on what we've done so far to include adaptation into our models or into our model and what kind of data we've used and what kind of data would really help improve it into the future. Now, I'm an ecological modeler, not a geneticist, so please bear with me when terminology is not 100% on point. So first I want to go into the difference between phenotypes and genotypes. Genotypes is what's actually encoded on the genes. Phenotype is what we see. So that can be the color of the flowers that we see on the screen here, or it could be the thermal tolerance of a coral. And it's important to note that genotypes are very difficult to model. There's really complex models out there that are attempting that. And with something like a thermal tolerance, we're probably looking at that being associated with more than 100 loci. So it's really incredibly difficult to model the genotype itself when we're trying to combine it with an ecological model. Phenotypes are a lot easier to model. And interestingly, they're also what's actually currently used a lot for evaluation of thermal tolerance in experiments, for example, because that's what you can see when you're exposing corals to different temperatures. So that's what we're modeling. We're not trying to actually represent the genotype. The model, as you just heard, is scape that we're using here, and it's for within reef populations. You've seen something very similar to this before. So we start off with a population with corals of different sizes. We run them through the growth, mortality, and reproduction, and then we receive a new population at the end of the year. But we're not going to keep it this simple now. We're going to add one more thing, and that is now we're going to have thermal tolerance classes as well as size classes. So what that means is we no longer just have the blue corals, but we also have orange and green corals. The orange corals, they're now less thermally tolerant than the main, which is the blue ones, and the green ones are more thermally tolerant. And it directly relates to their bleaching mortality. So this mortality has been calculated based on some of the previous bleaching events, and you can see in blue the average curve that we can find on the GBR. So if we have a low degree heating weeks, we're going to have a low mortality. As degree heating weeks increase, the mortality increases up to about 100%. Now the less thermally tolerant coral are going to have a higher mortality for the same degree heating weeks. And the more thermally tolerant are going to have a lower mortality. Now that's going to change over time as the population experiences different bleaching events. It's going to change the composition that we see out on the reef. But if we want to model coral populations over multiple generations, the first thing we really got to consider is heritability. So heritability relates to the difference between what we talked about before, phenotype and genotype. Not the full thermal tolerance is it encoded on the genes. There's other things feeding into it, like the environment. So not everything is going to be transmitted from one generation to the next. We're only going to submit, probably just going to transmit part of that thermal tolerance to the next generation. On the right-hand side, you see a couple of graphs that are related to that. So we commonly use the breeder's equation to do this, to go from one generation to the next. And the main thing we're looking at here is that heritability, which is generally assumed to be about 0.3 for polygenic traits that are non-morphological and related to fitness. So what that means, we're only transferring about 30% of that thermal tolerance to the offspring. So that becomes really important when we're looking at how that thermal tolerance can spread through a population and in recovering populations. So let's put those two things together. We're now going to look at the mortality from acute heating events, and we're going to look at the heritability. So we start off with a population of adults. And here we can see the thermal tolerance classes. So in this case, you see them from -3 to +3, and our population is distributed within those classes. Now, when we have a bleaching event, a degree heating week event, we can see some of these corals are going to die. Obviously, the ones with a lower thermal tolerance are going to die faster. So in this case, we're only going to have corals left that are in 1, 2, and 3. Now, if those could just grow on their own, that would be great. So much more resilient for the future, right? Unfortunately, that doesn't work. So we need to use that breeder's equation to see what the next generation would look like. But we didn't stop here, because the next step we did first was run our population through the early life history. So we got the distribution of the larvae if we didn't have a bleaching event. The reason why we're doing that is because we want to take into account the fecundity of those different corals, because remember, we also have size classes. So small corals are going to produce a lot less larvae than large corals. That means they're contributing to the gene pool of next year a lot less. So by using the larvae distribution instead of the adult distribution, we're taking that into account. We're using the same process for our population post the bleaching event. So now we have two different distributions for the larvae, one pre and one post. And we can apply the breeder's equation to that. So here you can see how a distribution would look after that heritability is applied. And you can see that the next generation is not actually as tolerant as we would have liked them to be after that selection event. They've gone a lot further, like back to that original. And so that's something really important in mind when we're trying to do these restoration actions. But what I started off with here is really important, and that is the initial distribution of the parents. We've got to start somewhere, right? And so what we actually need is how tall are these bars? How widespread are they? What's the maximum, what's the minimum of thermal tolerance that we currently see? And so we've based the spread roughly on a normal distribution, but with a cutoff, because normal distributions obviously are infinite, so we have a cutoff value, because I don't think anyone believes that corals right now are infinitely tolerant to thermal pressures. What we used to actually get this distribution specifically is a paper that was published in 2022. And it looked at the bleaching mortality index for different degree heating weeks. And you can see here on the plot on the left-hand side, we have in red the least thermally tolerant coral, and then in blue we have the most thermally tolerant coral that they had in their experiment. And you can see the difference here is that delta degree heating weeks, which is that span between the lowest and the highest thermally tolerant. And that was about 4.8. If you look at that and then back to the distribution, in red, that negative 2.4, in blue, that positive 2.4, that's your 90th percentile, and it directly relates to that data. Now, with the cutoff, we roughly looked at that data as well, but it's a lot harder to get that information out of that same kind of data. And part of that is because of how that study was set up and some of the limitations of that study. If you're looking at that plot again, you can see the highest degree heating weeks we have is about 9.8. And so what that means is that blue line of the most thermally tolerant is pretty much cut off at about 30% mortality. So we had to extrapolate it up to 100% to actually put it like as would be the equivalent of what we have in our model. That is high uncertainty. We need to look at much higher ranges of degree heating weeks to be sure of those cutoffs. And even the spread, the degree heating of that normal distribution is highly influenced by how that study was set up. So let's have a look at, if this distribution is highly uncertain, let's have a look at what that actually means in terms of seascape. Oh, sorry, so this is the standard deviations that we ended up deciding on, which is 1.89 and a cutoff of 8. So here's some results. And this is an example that looks very similar to what Juan showed just before. And so you can see all these different lines here represent different climate features. So they're not the different sites as Juan showed them, they're the different climate features now. And in orange, you can see the mean across all of those features. On the y-axis, we have the thermal tolerance deviation. So that relates to our thermal tolerance classes. You might notice we only have the positive ones there, not the negative ones. They were in the model, they just didn't become dominant. So I just cut them off the graph, because as you can imagine, thermal tolerance is not going to go down. And so you can see here, with a standard deviation of 1.89, we can reach about 4 degree heating week thermal tolerance by the end of the century, or an increase of 4 degrees thermal tolerance. But if we change the standard deviation to 2.49, that changes, and we can get up to about 5 degree heating weeks. So the speed is a lot faster, and the final tolerance reached at the end of the century is a lot faster. And that does have quite an impact on our coral covers across time as well. So it just goes to show that we really need to do a bit more research in that field. Now the second thing I'm showing here, that is the cutoff. So that's the second value that we needed to look at. And the top one here is 6, so a little bit lower than what we just looked at before. And the bottom one is 10, so that's a bit higher than we looked at before, because I wanted to show you a little bit more extremes of what you could be looking at. And you can see it makes a dramatic difference. Everything is faster, everything goes a lot higher by the end of the century. So that cutoff becomes really important to our model predictions. And you can think of that as, so the more thermal tolerance we currently have available, the more we have left in that really wide tails that can produce offspring and then push up the thermal tolerance across time. Now, these are some of the concepts that we put in so far, but there's another one that we've included, and that is the emergence of new phenotypes. Now, what that's meant to represent is gene reorganization, mutation. It could include a whole heap of different concepts. The general gist of it is that now we can have individuals that are outside of the cutoffs of what we're setting for today's population. It's not unrealistic to think that that's going to happen, but it's probably not going to be very common in the 90 to 100 years that we're currently predicting. And so what it means is we're going to have a proportion of the larvae is independent of that process that we just talked about of selection and heritability. We're just allowing it to be somewhere in those red areas, so somewhere outside of that cutoff in that normal distribution. But that proportion is probably very small, so less than 1%. At this point, this part of the model has only been set up based on conversations and general ideas. There's no data that's fed directly into it. So it's a highly uncertain process. We're just playing with it at the moment to see what kind of impact it has. At this point, it doesn't have a huge impact. Again, we're looking at 90 to 100 years. Things like mutations are not that common in that short time frame. If we were predicting for 500 years plus, it probably would play a bigger role. So let's go back to the original question I had when I started all of this. What do we actually need to model adaptation? And so on the right-hand side, you can see a bit of a word cloud. The reason why it's there is because we actually need a whole heap of bits and pieces. It's not one thing that's going to solve everything. But what I think we really need is we need to be talking to each other, because there's this study, and there's a lot of other studies that we've looked at as well to parameterize some of these parts of the model that are not necessarily designed to feed directly into our model. And that's because there hasn't been a conversation. And that can mean that they are in units that are not appropriate for us to use, or they just have some other characteristic that make it really difficult for us to actually uptake that data. And it's so useful, like there's so much good research done. It would be great if all of it could feed into our model so we can use it to evaluate interventions. But what we need, so this is the general gist of it. So we need to talk while we're having a study design. But the specifics of what we need is we need more information on that initial distribution. We saw how much impact that has. We really need to be looking at that in more detail. And specifically, what would be great if we had is different location across the GBR. The study we're currently using is from a single location. And also, we would love it to have that distribution for different species, because right now, it's all based on acropora. So, and as we saw before, the model itself is already, like from Juan's talk, the model itself is already producing differences for different species. So it is quite likely that there is also difference in tolerance out there right now. And then the final thing that we need, I put it here as a little number 2, is how the new phenotypes emerge. Realistically, we still need to know everything about that, but it doesn't have as big of an impact, so that's why it takes the second place there. Thank you very much, everyone. And if anyone has any research that could feed into that, feel free to reach out to me at any point in time. Thank you very much.
Maybe just time for one really quick question. And you're more than welcome to catch her during the... yeah, Cynthia.
Thanks, Vanessa. That was really interesting. Oh, thanks, Vanessa. That's great. Just out of curiosity, and you might not know the answer, how low do some of your population sizes fall to during some of your simulations?
So when we're looking at some of the high SSBs specifically, they go to 0.
Okay.
So we definitely have gotten that. And then it becomes so, it's really interesting because sometimes you can see these huge spikes in thermal tolerance and it's like, yay, they're all going up. That's because there's only 5 corals left and they were highly tolerant. So it's not particularly useful to have that big spike. So you got to be very careful when I'm presenting these averages. I'm being very careful to not include necessarily always ones where populations are really, really small and we have very little coral left.
Okay, thanks.
Thank you so much, Vanessa.
Thanks.
Very nice